Okay, welcome. In this video, we're going to start talking about arcs and angles and their relationships. So the first thing you need to know is that there is a relationship between angles and the arcs they intercept. Intercept. So think of the word intercept like the y-intercept, right? That is where it intersects the graph. So intercept is kind of like saying intersect. So if we're talking about an angle and the arc it intercepts, let's look at our first one here. Here is the angle. And the arc that it intercepts is this arc right here. All right, so in this video, we're going to specifically concentrate on when the vertex is on the circle. Okay, so in these two images below, you can see that the vertex is on the circle. Let's find the vertex on each of them. So the vertex for the circle on the left is M, and the vertex for the circle on the right is A. Okay, now I need to give you a vocabulary word here. So the definition of an inscribed angle, an inscribed angle is an angle that has its vertex on a circle and its sides contain chords of the circle. Okay, so chords. I want you to go ahead and underline that as well. That's important because not both of these are inscribed angles, right? So we have this angle on the left here, and then we have some angles over here. But not both of them are inscribed, or not all three of the angles that we see here are inscribed angles. If you look, it has to contain chords of the circle. And remember that a chord is a line segment with its endpoints on the circle. Right? So if I look over here, the side of this angle contains or is contained in this chord, right? There's the chord right there. This side is also contained in a chord, right? It extends past the chord, but there is a chord there that's part of that side. Okay, that's different than this one over here, because over here, let's talk about angle 1. Right, here's angle 1. This side of angle 1 is a chord, but this side of angle 1 is contained in a what? It is not called a chord, this is a tangent. Okay, so this is not an inscribed angle. This one over here is an inscribed angle. However, I like to teach these at the same time. Even though they're two different types of angles, they both have their vertex on the circle, and they're both going to follow the same formula. So you can just remember them together. So let's make a little note here that this is an inscribed angle. And this one, not inscribed angles. Inscribed angles. Okay, so now let's get into how we're going to use these. Okay, you don't need to draw any of this, but I want to show you how this all works here. So we have an inscribed angle whose vertex is on the circle and whose sides are contained in chords, and we have its intercepted arc here in red. And we want to know what is the relationship between this measure and this measure. Okay, and so looking at it, it does not look like it's 100 degrees, right? If you think of this, this is an acute angle, 100 degrees is an obtuse angle. So it cannot be the same, but what is the relationship? Let's see what we can figure out here, what we already know. This angle, see there's a dashed line in here, is a central angle. This we've learned about is the same as the intercepted arc. So this angle here is 100 degrees. So if you can, why don't you pause the video and see if you could come up with how to find the other angles. And if you're unsure, you can just continue watching. So there was a long time ago, we learned that these, what we call remote interior angles, these are the remote interior angles, must add up to this exterior angle, right? If we have a triangle, sorry, let me point out that this is a triangle here, right? That's a dashed line, but it's a triangle. And this out here is the exterior angle, and these are the remote interior angle, and these are congruent. Why are these congruent? Well, these two sides have to be the same because they are the radii of the circle. And the sum of these two angles, remote interior angles, equals this exterior angle. And since they're the same measurement, well, then they both have to be 50. All right, so we have 50 degrees here, and we have 50 degrees there. So now let's look at what that relationship is. This angle is half the size of the intercepted arc, and we were able to figure that out because we happen to have it right in this position where it's the diameter and use this triangle, but I'm going to let you know that it actually stays the same. If I were to move D somewhere else on the circle, you would still see that this angle here would remain half of this intercepted arc, because as I move it around, this angle is going to get smaller while this angle gets bigger, therefore this angle stays the same. So I don't know if that made sense, but let's go ahead and watch it move around here if I can get it to work. Okay, there we go. So no matter where I place the D, the vertex, as long as it's on the circle, it's half of this arc here. Right, now as I change that arc, so then I have to make this arc, let's say 152. Well, then over here, this angle is half of 152 is 76. All right, so let's jump back to our notes and put this in there, the actual formula. Okay, I went ahead and wrote the words in there for you, and I would go ahead and write that down because it just writes it nice and clearly there. But the measure of the angle is half the intercepted arc. So go ahead and pause and get that in there. And then I'm going to use these pictures to actually write a formula. So for this circle on the left, we have the measure of angle LMN equals 1/2 the measure of arc LN. Now, while these angles on the right are not inscribed angles, they still follow the same rule. So let's go ahead and write these formulas out as they would pertain to this drawing here. So in this case, the measure of angle 1 would equal 1/2 the measure of arc AB. So that you can see that we have the measure of angle 1, and then we have the arc AB. So I'm going to put that in the same color there. Same is true for the measure of angle 2. All right, so the measure of angle 2 equals 1/2 the measure of arc ACB. Which should hopefully make sense because the measure of a straight angle, right, this whole angle here is 180 degrees, right? The measure of the whole angle here is 180, so the measure of angle 1 plus the measure of angle 2 equals 180. And the measure of all the degrees around the circle equals 360, and half of 360 does equal 180. All right, that is the correlation when the vertex is on the circle.